I'll be presenting our project on a miniature steam generator prototype. Before we begin, let's briefly understand the concept behind it. Thermodynamics is the study of energy, heat, work, and the relationship between them. One of its most important applications in engineering is energy conversion. According to the first law of thermodynamics, energy cannot be created or destroyed. It can only be transferred or converted from one to another. Our prototype demonstrates this by converting heat energy into steam energy, then into mechanical energy, and finally into electrical energy. Energy conversion is a fundamental principle of thermodynamics and has played a significant role in the development of modern engineering. In power plants, a steam generator converts heat energy into steam by heating the water. The high-pressure steam is then used to drive a turbine or piston, producing mechanical motion that can be converted into electrical energy. Inspired by this concept, our project develops a small-scale steam generator prototype to demonstrate the same energy conversion process. Through this project, students can better understand how thermodynamic principles are applied in real engineering systems and appreciate the importance of efficient thermal energy conversion. The main objectives of this project are to design and manufacture a miniature steam generator model that is capable of producing steam to operate a mini steam engine. Through this prototype, we aim to apply the first law of thermodynamics by demonstrating the conversion of heat energy into mechanical energy. We also investigate the relationship between heat input, steam production, and mechanical energy output. Besides that, this project helped improve students' understanding of energy conversion through practical experiments. Finally, the prototype is designed to be educational, safe, simple, and economical for learning purpose.
Hello, I am Akid, and now I'll be discussing about the materials, sustainability, and design process of our prototype. So let's begin with the materials and apparatus that we use to build our steam generator. First, we utilize an aluminium soda can to act as a boiler. Then we use a medical syringe to function as a piston and cylinder. For the flywheel, we use a CD, and a stiff metal was used as the connecting rod. The base and support was constructed out of a cardboard. So to connect the boiler and the syringe, we use a brass nozzle. The connection was properly using epoxy putty, and hot glue was applied to secure the various components, and we use a standard wax candles as our heat source. Finally, a DC motor was utilized as an electrical generator. So we made sure that the aluminium, the CD, and the cardboard were reused and will not be discarded. And this approach also helped us minimize our environmental impact, and furthermore, it significantly lowered the overall construction cost of the project. Moving on to our design process, here are the steps that we took to assemble our prototype. First, the aluminium can was prepared to serve as the boiler. Next, a brass nozzle was fitted to the can and carefully sealed with epoxy putty. Then we placed a measured amount of water inside the can. After that, a syringe was securely attached to the brass nozzle. The plunger of the syringe was then connected to the CD using a stiff metal wire, and we mounted the CD directly to the DC motor shaft. After the components then aligned and secured onto our cardboard base, finally the boiler was elevated to provide enough space underneath for the candles. For the thermodynamic system identifications, our prototype is analyzed as closed movable boundary system. We assume there is no steam leakage, meaning the mass of the working fluid remains inside the system. In this system, the heat enters from the candles. The expansion of the steam moves the syringe piston, which produce the boundary work. As the piston moves, it creates a changing system volume. Our defined system boundary includes aluminum can, the water steam, the brass nozzle, the syringe volume, and the face of the plunger. That's all from me. Thank you.
I will explain about our prototype demonstration. So firstly, we will light up the two candles under the aluminum can. The aluminum can contain like half tin of water. After waiting around 10 minutes, the water will start boiling and produce steam. The steam will come up from a small hole connected with the syringe with a certain velocity. Then the steam will push the piston inside the syringe. As the piston is connected with the CD, so it will start rotating the CD. And during this process, they will have inertia of the CD. By combining the steam force and the inertia force, it will make the CD start rotating with a moderate speed. I will show the video demonstration in the next part. The CD is connected with a DC motor, so when the CD is rotating, the motor will produce electricity. So this one is the main point that we want to elaborate in our project.
Now I will explain the real-life application of our prototype. The basic energy conservation principle demonstrated in our model is used in many large engineering systems. In steam energy, high-pressure steam moves a piston or rotates a mechanical system in thermal power plants. Fuel in burn to heat water and produce steam, which rotates a turbine connected to an electrical generator. Nuclear power plants use heat from nuclear reactions to produce steam, while geothermal power plants use heat from the beneath the Earth's surface. The same principle is also applied in concentrated solar power plants, industrial boilers, marine propulsion system, and waste heat recovery system. Although our prototype is much smaller, it demonstrates the same basic process. Thermal energy produces steam creates mechanical motion, and mechanical motion can be converted into a electrical energy. To conclude, our miniature steam generator prototype successfully demonstrated the practical application of the first law of thermodynamics. Heat supplied by the candle increased internal energy of the water and produced steam. The expanded steam pushed the syringe piston and the connecting rod convert this linear motion into the rotatory motion of the CD flywheel. The rotating flywheel then drove the DC motor, demonstrating the conversion of mechanical engineering into electrical energy. The prototype was analyzed as a closed, movable boundary system, assuming that so steam leaked from the sealed connection. Throughout the process, energy changed from the chemical energy to thermal, steam, mechanical, and electrical energy. Some energy was also lost through heat transfer, friction, variation, and vibration and electrical resistance. Although the prototype produced a small output, it successfully connected thermodynamics theory with a practical engineering application. Future improvement in sealing, insulation, alignment, and measurement instrument could improve and performance.